probability of error PF is equal to 0. So now let's see how it performs. In other words, we are going to derive simple expression for utilization, link utilization or channel utilization, whatever it is. So you can see the timing diagram here. Let's say this is the time. Okay. So you can see that a frame is transmitted in stop and wait, and this is the time the last bit is transmitted, right? And that last bit should go to the other end of the link. It takes TP time units. So here, let's say this is TP. So when the last bit is received at the other side of the link, acknowledgement is transmitted, and the acknowledgement will take another TP time units to reach the sender. Once the sender gets acknowledgement, it sends the next frame it transmits for TF duration. Then it waits. So this is the waiting time, waiting for the acknowledgement. Then the next frame is transmitted. Okay? So here you can see that the total time the link is engaged or used for this protocol is this. This is the total time, which is cyclic, which is repeating. Out of this total time, TF is the time for which the link is used for useful transmission. Right? So utilization is TF divided by the T total. T total is TF plus 2TP, okay, because the total time is TF plus 2TP. We assume that the acknowledgement transmission time is negligible. If you want to add the acknowledgement transmission time here, then the denominator will have acknowledgement transmission time as well. So this is equal to 1 by TF by TF plus 2TP by TF. This is 1 by 1 plus 2A. Very simple. And easy to remember as well. So utilization is 1 by 1 plus 2A, where small a is TP by TF. Okay? Now let's consider the case of errors. Assume that, okay, there's a small chance or some chance for errors, which is given by PF. So if there is an error, there will be retransmissions, right? So instead of 10 frames, you may end up with transmitting 11 frames or 12 frames, right? Instead of 100 frames, you may end up with transmitting 105 frames. Why? Because 5 frames were damaged. So we had to retransmit 5 frames. So if the probability of error is more, obviously the chance of retransmission is more, and the number of retransmitted frames will be larger, right? So on an average, how many times a frame is transmitted? That's what we are going to look at. If there is no error, if 10 frames are transmitted, only 10 frames will be transmitted. If the message has 10 frames, only 10 frames will be transmitted. But if there is an error, instead of 10 frames, we end up with transmitting more than 10 frames. Okay? So on an average, okay, a frame is transmitted more than once. Some frames are transmitted once, some frames are transmitted 2 times, some frames are transmitted 3 times, 4 times, 5 times, right? So what is the average number of times a frame is transmitted? That's what we are going to derive first. That is, NR is the expected number of times a frame is transmitted. Okay. So this we will show that NR is equal to 1 by success probability. Okay. So number of times a frame is transmitted is 1 by what P success. Okay. If P success is 1, that means if there is no error, every frame will be transmitted only once. But if P success is less than 1, okay, on an average, a frame is transmitted more than once. So how do you find this average? Okay, let's say this frame is, okay, how many frames are transmitted once? Let you take 100 frames. Maybe 95 frames are transmitted once, right? One frame might have been transmitted twice. One frame might have been transmitted thrice. So you can easily calculate the mean number of or expected number of times a frame is transmitted. Okay? So I used to give analogy. So let's take an analogy to better understand this NR is equal to 1 by P success. You take the coin tossing example, right? So let's say the success means getting head. You toss the coin. Okay, you are interested to get the head. How many times you need to toss to get the head? Right? Right? When you toss, sometimes you just one time you tossed, you get head. Right? Sometimes you may have to toss 2 times, tail, head. Sometimes you toss tail, head, 3 times you tossed. Correct? So you repeatedly do it. On an average, how many times you have to toss the coin to get a head? Is that clear? Is my question clear? Can you tell me how many times a coin need to be tossed on an average? If you take an average. You take a coin, you can try yourself 100 times. Let's say first you try. Okay, you might have got head first time. Okay, mark it first time. Experiment number 1, I got it first time. Experiment 2, I got it first time. Experiment 3, maybe I got it second time. Okay, is that okay? So how many times you need on an average or the expected number? Okay, now let me give another analogy. Okay, let's say you are going to write a test. Okay, MCQ based test, not my test. Okay, and you go to the test center. Okay, each question has 4 options, A, B, C, D, right? And you didn't prepare anything. You cannot understand the question at all. Not my quiz. Okay, I believe my quiz you should be able to understand, right? Okay, A, B, C also you cannot understand. So you decided to choose answers randomly. Assume that there are no negative marks. Okay? You decided to choose answers randomly. Okay, and also assume that okay the correct answer is also random. I mean they are not biased. Right? So then on an average, how many attempts you need to make to get one answer correct? Now you look at 2 examples, right? The first example, how many times on an average you need to toss to get a head? It's an average, right? Expected number, right? It's not the actual, right? Okay. Then second question, a test has 4 choices, MCQ based questions. So how many questions on an average you need to attempt to get an answer correct? Yes, any answer from you? For the first example, yes, 2. Second example, 4. Okay. So now you can try to relate it, right? The first example, success probability is 0.5, right? Second is success probability is 0.25. Assume that every choice is equally probable to be a correct answer, right? Okay. So number of times a frame has to be transmitted will be, including retransmissions, will be 1 divided by P success, right? So now instead of now this expression will change. TF, the total would be NR times total, because each frame is transmitted NR times. Each frame is transmitted NR times. So this will be NR multiplied by TF plus 2TP. That's equal to 1 by 1 plus 2A NR. NR is 1 over success probability. So this is equal to P success divided by 1 plus 2A. Right? So if there is no error, the answer is 1 by 1 plus 2A. This is link utilization. If there is an error, okay, you just multiply it by success probability. That's all, half a frame. Is that okay? Success probability divided by 1 plus 2A. That's all. So success probability is nothing but 1 minus PF, because PF is the error probability. Any doubt? Next, we are going to analyze the sliding window protocol. Sliding window analysis is slightly more complex compared to the previous one, but the result or the expression is also easy to remember. Okay. Now, in the case of sliding window, what happens? The sender can send or is permitted to send up to W frames without waiting for an acknowledgement from the other side. It doesn't need to stop transmission just because it did not receive the acknowledgement. But it has to stop transmission, okay, when it has already exhausted the window, okay, window is 0, okay, but it has not got an acknowledgement from the other side. In that case, it will wait. Is that okay? Then it all depends on when it is getting the acknowledgement. So for analysis purpose, let's assume that, okay, every frame is acknowledged. Every frame is individually acknowledged, right? And you can easily extend to cumulative acknowledgement. So let's not worry about it, right? So at what time it will get the first acknowledgement? The first acknowledgement, the sender will get at TF plus 2 TP, right? The second acknowledgement, it will get at TF plus 2 TP. Because the second frame is transmitted at 2F, it first transmits first frame TF, it doesn't need to wait for the acknowledgement. It transmits another frame TF, 2TF. By 2TF, the second frame transmission is done. So the acknowledgement for the second frame would be back at 2TF plus 2TP. Correct? Similarly, third acknowledgement will come at 3TF plus 2TP. So for every TF, an acknowledgement is coming back. But the first acknowledgement comes back at TF plus 2TP. But before the acknowledgement comes back, what will happen to the window? Whether the window will be exhausted or not, that's the question. So now we identify two cases. The first case is WTF. What is WTF? At TF, first frame is transmitted, 2TF, second frame is transmitted, 3TF, third frame is transmitted. At WTF, W frames are transmitted, right? So at WTF, all W frames are transmitted if it is greater than or equal to TF plus 2TP. TF plus 2TP is the time when the first acknowledgement comes back, correct? So if WTF is bigger, that means by the time the acknowledgement comes back, the window is not empty. Still, okay, it is not empty. Window is bigger. WTF is bigger than the time when it receives the acknowledgement. So it will expand it, right? So this is illustrated in this example. Let's say W equal to 5. So this is TF, 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 TF. So this is the time the window, okay, will be exhausted if no acknowledgement was received, correct? But if TF plus 2TP is such that, maybe TP is small, okay, such that TF plus 2TP is here. That is the first acknowledgement comes back here. Then the window will expand, right? Then you can see here for every TF an acknowledgement is received. Next acknowledgement will come here, here. So window will keep expanding. It will never become empty. It will never become empty, right? So it can continuously send data. When it continuously sends data, if you look at the link, okay, the link will be continuously occupied by the bits, right? So you take a bridge, if all the time, okay, it's full of cars, then it is fully utilized, right? You take the bus, all the time the seats are full, fully utilized. Lecture theatre also, if all the time it is fully utilized. Otherwise it is underutilized, right? So now the transmission takes place continuously, no waiting time, no gap. So utilization is 1. Utilization is 100%. No wait time at all. Now look at the other case. WTF is smaller than, okay, when WTF is greater than or equal to TF plus 2TP, that's the same as W greater than or equal to 1 plus 2A. Agreed? Because you divide both sides by TF. That means W greater than or equal to 1 plus 2 TP by TF. TP by TF is A. We know A is TP by TF. Is that okay? So what we need to do is, you need to check, okay, let's say W is given, TP-TF is given, so we need to check W is greater than or equal to 1 plus 2A. Yes, means utilization is 100%, 1. Now, look at the other case. This also can happen. WTF is less than TF plus 2 TP. That means the acknowledgement takes more time to reach. WTF is the time when W frames are transmitted. So it is lesser than this. That means by the time acknowledgement comes back, the window has already been exhausted. Window is already empty. Now look at this example. Here we assume W equal to 3. So first frame is transmitted here, 2TF, 3TF. Third frame is transmitted here. But the propagation time is quite long, such that TF plus TP is here. TF plus 2TP is here. The acknowledgement comes only at this point. So this is the waiting time. Because at this point, window is 0, empty. So during this time period, no transmission. Now, at this point, acknowledgement is received, it's expanded. Then it transmits a frame. The second acknowledgement will come back here, TF plus 2TP. So next acknowledgement it comes back here, it will expand. Next acknowledgement will come back here, it will expand. That means this acknowledgement is for this frame, this acknowledgement is for this second frame, this acknowledgement is for third frame. Now, for this frame, the acknowledgement will come back only here. Because this is TF plus 2TP. So, if you use the formula, we can say that WTF is the useful transmission for every TF plus 2TP. That is U. That is given here. Useful transmission time divided by total time. We use the link. Right? WTF is the useful transmission time. This for every TF plus 2TP. So this is cyclic. It's repeating. Right? So the utilization is W divided by 1 plus 2A. Very easy to remember. Even if you forget, you can quickly derive it. It's not a big deal, right? So stop and wait. There's no question of window and other things because window size is 1 in stop and wait. Utilization is 1 by 1 plus 2A. For sliding window, you cannot immediately write the equation, right? You need to check if W is greater than or equal to 1 plus 2A, utilization is 1. Otherwise, utilization is W divided by 1 plus 2A. If you want to incorporate the errors, you just multiply it by success probability. So here you can see if W is greater than or equal to 1 plus 2A, okay, this one. If there is no error, utilization is 1, right? If there is an error, you multiply it by success probability. If there is no error, this is no error. If there is no error, utilization is W by 1 plus 2A. And if there is an error, okay, this will become this. Same thing, W divided by 1 plus 2A, but you are multiplying it by success probability. Is that fine? Very simple. 1 or W by 1 plus 2A. No error. If there is an error, you multiply it by success probability. Okay? For go back N, the derivation is a bit more complex because we retransmit not only bad frames but also good frames. It becomes complex. I omit the derivation. I'm not going to derive an expression for this and all, okay? And you don't need to memorize, particularly go back N from the test point of view. If there is any question, I'll give you the formula, okay? But for selective reject and stop and wait, I would expect you to remember, or maybe within half a minute or 1 minute, you should be able to derive it. It's not difficult to derive, okay? Any doubt? As I said, the acknowledgement time is not included, but if you want to include acknowledgement transmission time, then the denominator will change. It will be TF plus 2TP plus acknowledgement transmission time, right? So that means as part of the test or exam, if you are given acknowledgement carries 100 bytes, that means you should not ignore it, correct? So you need to calculate acknowledgement transmission time. You need to add it in the denominator. But this expression will be the same, TF divided by TF plus 2TP, but with the addition of acknowledgement transmission time at the denominator. Let's move on to lecture notes 5. So this is on Ethernet. I follow these two books, Peterson Davy, I think for most of them, and for some part I'm following Gross and Rose, particularly for VLAN part. Okay, so you will understand when I teach this. Again, as I said, you are free to follow any of these books. They are tell the same thing, maybe slightly different way, right? Okay, it's up to you. Whichever book you feel comfortable, use it. Okay, and for me, if you go through the lecture notes, it should be sufficient for you to understand. But at the same time, I would definitely recommend to read the books for a better understanding, right? Is that okay? When we say Ethernet, okay, there are two types of networks. One is broadcast LAN, the other one is switched LAN. So it's used in local area environment. Okay, still we are in layer 2. Ethernet is a layer 2 network. Okay, so we are going to look at two parts. One is on broadcast LAN, where there is a possibility of collision. So how to deal with collisions. So we are going to look at. The second part is Ethernet switches. Okay, with Ethernet switches, we can build a switched LAN, a switched network. So what kind of protocol is used there, okay, for frame forwarding, etc. Okay, particularly we are going to look at spanning tree based protocol. Okay. We start with the MAC. Just a quick recall, we already, I think, spent some time in lecture notes, part of lecture notes 1 and 2, okay, about this MAC, medium access control. So whenever medium is shared by more than one, right, there is a need for MAC, medium access control. Okay. And okay, nowadays Ethernet or our system may be mostly connected to Ethernet switch, but still traditionally we use the term MAC, at least to tell the address, MAC address, right? The hardware address, MAC address. So if you look at specifications, you see the MAC address. Doesn't mean that your computer should only broadcast. Okay, it can be connected to switched network as well. Okay, this I think figure we have already discussed several times. Okay, just a quick recap. So there is a channel or link which is shared. So we in the network context we call them as bus, shared bus. But it's not within a computer or something. It's a cable on the, okay, installed on the wall or something. But I don't think nowadays you use it. I mean, you don't prefer to use it also in the campus, right? You prefer to use Wi-Fi, right? Maybe when you go to the lab, connect it, their network is there. But nowadays we use switches. But historically, this is the evolution which we are going to discuss. Okay. So there is a medium which is shared. And our systems or computers are connected to this. So there will be some sockets and connectors, network adapters are inside, right? So it could be 10 Mbps or 100 Mbps, but what is to be noted is that it's a broadcast medium and only one is permitted to send at a time. So let's say B transmits, and usually we use half duplex cable in the Ethernet, not switch. When I say Ethernet, I mean I just refer to the old or traditional Ethernet, okay, which late 70s or 80s. Okay, so they developed in maybe 80s popular. They were popular in 80s. Then 90s how becoming popular. Then 2Ks, I think switches. Okay, slowly they become popular, and now the most popular ones are switches because they are also cheap. Okay, so when they become cheaper and cheaper, we tend to use those devices more and more, right? Okay. So but still the adapters, okay, they are compatible with the shared medium network, so they use some protocols in the event of collisions and other things. Okay? So in this case, it's off T plus. Off T plus means A can communicate to B can communicate to A, but not at the same time. Okay? So here, whatever B is sent, the signals will propagate in both directions. So eventually it will reach all the nodes in the network. And there will be terminators at both ends that will terminate the signal. Okay, so the signal cannot just vanish it. Okay, there are terminators to vanish. Okay, so they cannot, back and forth cannot traverse. They are terminated at the end nodes. But Ethernet, okay, as I think I was mentioning earlier, there's no coordination in Ethernet. Everybody is a boss. They don't want to coordinate among themselves. Okay, they are independent. So it may so happen that more than one node or system can try to transmit at the same time. So in that case, there will be collisions. Let's say B also transmits, D also wants to transmit. If B knows that it is receiving something, some signals, it won't transmit. There's no point in transmitting because it's already receiving. But it may so happen that the B signal was here somewhere, okay, D is not aware of it, so D might think that there is no transmission ongoing, it may also start transmitting. So if more than one system transmit at the same time, the signals will propagate both sides, they will collide, there will be collisions. That means bits will be damaged. So the frames become useless, right? And another important thing is that the total data rate or bandwidth, okay, would be limited to 10 Mbps in this particular example. Okay, if the shared Ethernet capacity is 10 Mbps, even though every node can transmit at the rate of 10 million bits per second, they will not be transmitting all the time, right? You take 1 second time period, I think this example I have already given, you take any 1 second time period, maybe A might have transmitted NA number of bits, B might have transmitted NB number of bits, million bits. Okay. Note that when A transmits, it will transmit at the rate of 10 million bits per second. But A might have transmitted only for 300 milliseconds. That means it has, even though it transmits at the rate of 10 million bits per second, because it transmitted only for 300 milliseconds during that 1 second period, that means it has sent only 3 million bits. Right? So if you add everything, it cannot exceed 10 million. That's why we say that the bandwidth is shared. Okay? And they are usually used in local area environment. They are not used in wide area metropolitan where, okay, they can transmit 100 kilometers, 1,000 kilometers and all. No, not possible. Ethernet, okay, is standardized IEEE 802.3 standard. So that is popularly used, that's popular. There are different variants. Nowadays, switches are more popular than the basic Ethernet, traditional Ethernet. Anyway, slowly you'll understand that. Token ring, as I was mentioning earlier, promoted by IBM, was a tough competitor once, but no longer they are popular. No new developments, okay. I don't think any active deployments or anything is there. Right. Wireless, yes, popular, okay. So you'll be looking at wireless network, Wi-Fi, okay, and wireless LAN next week. Right? This week we focus on wired local area network based on Ethernet. So Ethernet, okay. In terms of cables, okay, if you look at the Ethernet, traditional Ethernet, that is 80s, okay, talking about 1980s or late 70s or 1980s. So during that period, okay, this was quite popular. This was the first Ethernet. We call it as broadcast Ethernet. And this is how the connection, they are connected. This is how the different systems are connected in the lab or etc. Okay. At that time, there was no home network and all. Maybe some network could be there in some universities, okay, not all universities, okay. It uses coaxial cable. I'm not going into the detail. Coaxial cable is similar to the TV cable. It's off duplex. and initially it was transmitting up to 10 Mbps. Okay, then 1000 Mbps adapters were evolved. The length can be 2.5 kilometers. Okay, that means a single Ethernet can span or cover maybe multiple floors or a big lab, okay, or if there are small rooms, small offices, it can span multiple floors. It can span multiple buildings also, as long as the total cable length is within 2.5 kilometers. So that is the standard. But nowadays, the trend has become the other way. We don't have a single Ethernet which supports 2.5 kilometer long, Ethernet where many systems are there. Instead, we may have switches and hubs which support small set of systems. Okay. Anyway, we will understand better later. So usually they are arranged into 5 segments. Okay. So that is, so the total length is 2.5 kilometer. Okay. But every 500 meter, we need a repeater. Repeater R, then R. Why? Because when the signal traverses beyond 500 meters, half a kilometer, there's a high chance of attenuation or damage for the bits. Okay, so we need what is called R, that is the repeater. Okay, so as per the standard, there can be, okay, if the network is small, within 500 meters, no need for repeater. Right? The maximum is 2.5 kilometer. In that case, you need a repeater for every 500 meters. So there will be 4 repeaters used. That's the maximum. Repeaters are not exactly like amplifiers. Okay, repeater will repeat the bit. When it receives 1, okay, that's in a bad shape, bad, okay, or poor 1. Okay, poor 1 is retransmitted as a good, a fresh 1, right? Okay, when it receives 0, that's already in a poor shape. Okay, so it transmits a fresh, a new 0 here. Okay, with full signal strength, etc. Okay, it repeats. 1 is repeated, 0 is repeated, but bad signal becomes good signal when it is repeated, so that it can traverse another 500 meters. Okay. Now this table, it's not exhaustive. It's only a small subset of different types or kinds of LAN. Right. So we are going to look at different types, naming convention, and some features of the LAN. Okay, what type of cables are used, okay, and how many systems it can support, etc. Okay. The first column shows the name. The very first, that is late 70s or 80s, those days, the first set of Ethernet or traditional Ethernets, they are called 10-base-5 and 10-base-2. There are 2 types of Ethernet initially were popular, 10-base-5 and 10-base-2. So what do you mean by 10-base-5? 10 stands for 10 Mbps. Okay, 10 stands for 10 Mbps. If you have 1000 in that place, it is 1000 Mbps, 1 Gbps. Okay, so 10 means the data rate in Mbps. 5 means each segment length can be 500 meters. Instead of 500, we simply say 5. Is that okay? Base means baseband signal. It uses baseband signal to transmit. So baseband signal, so if you look at the definition, okay, it's basically low pass, low, the frequencies are low frequencies, okay, so very low frequencies are not modulated signals. So with that meaning, base is used. Okay. And it uses a cable called thick coaxial cable. It comes with 2 different standards, thick coaxial cable and thin coaxial cable. So there will be dimensions, other characteristics which make them different. Again, we are not going into the physical properties of them. Okay, just remember that thick coaxial cable was used here. I think that sense it was also called thick Ethernet or something. Okay. So 500 meters, number of nodes per segment is 100. it can support up to 100 systems, computers to be connected in every segment. 10 base 2, it can support up to 200 meters. That means at 200 meters, you need a repeater. There's no way, right? Only 30 nodes can be there in the segment. Next, evolve 10 base T. This T stands for twisted pair copper wire. Okay? Because maybe in 90s, the hub-based Ethernet, they were evolving. Hub uses the configuration something like this. So this is a hub. It's a small box, okay, like our set-top box and other things. There's a small box you can imagine, okay, with multiple ports where different systems can be connected to this. Okay? So the connectivity here, we call it as star connected, something like that. Star, they are connected. Okay? And it uses the cables. The used here is twisted pair copper wire, like something similar to our telephone cable or LAN cable kind of cables. So that standard is called T. Maximum segment is 100 meters. You just see that, okay, within 100 meters. Because the configuration is hub-based, the distance between any two hosts is more or less same. Okay? It's not like bus. The bus, it's linear, okay? It should go like this, cables. So the distance between this computer and the last computer will be much larger when compared to the distance between this and this, right? But because it's star connected, like everyone is connected directly to the hub, the distance between these two and these two, they are not much different. There could be differences, but they are more or less close. Because let's say you have a hub there and all systems here are connected to this, right? The distance is more or less same. So that's why the maximum segment is limited to just 100 meters. But it can support up to 1024 according to the standard. You can have 1024 ports to support. And next, evolved F. F stands for fiber optics. So you can have fiber cables. So basically, they're used in switches. And again, 1024 systems. Ethernet maximum supports 1024 within a system, within a LAN, within one LAN, okay? And it can traverse up to 2K without the need for regeneration, okay? Because it's a fiber optic based, the attenuation is small. There are other standards. So later, here and there, I will mention some standards. But if you look at the literature or if you Google it or from internet sources, you can see there are several standards, okay? You don't need to memorize, but you should be able to understand what they mean. What do you mean by 100 base F? Okay, what that 100 means, what is that base means, what is F means, okay? Now let's look at Ethernet frame format. So if you look at this frame, so you can see that there is a header. So this part is the header. The header carries 48 bit. 48 bit means 8 byte address, destination address. I think this we have seen in lecture notes too, if I'm not wrong. The hardware address or MAC address or Ethernet address, okay, it has 8 bytes, right? 64 bits. So as part of the Ethernet header, it will carry 6 byte destination address, 6 byte source address, and 2 byte type or length. 2 byte type or length. It's very interesting. So it has two purposes. And the maximum number of bytes it can carry is 1500 bytes. An Ethernet frame can carry 1500 bytes. And how many bytes are carried is specified here, the 16-bit field, the length field. So basically it uses count-based framing. If 500 bytes are carried, this here, these 2 bytes will tell number 500 will be there. If 800 bytes are carried, 800 will be there. Okay? But if the value of this field is more than 1500, it can also happen. Then it doesn't represent the length, but it represents the type of the frame. Okay? By default, the frame is the normal data frame, right? But I think we have seen ARP, Address Resolution Protocol, right? By which within a network, everybody can send some ARP packets, request and reply packets, by which everybody within the network knows IP address and the corresponding MAC address, right? So we need to send some type of messages. That's also a frame, right? So to differentiate the normal data frame and, okay, it's a different type, let's say ARP frame, okay, we will specify this. So if the value is greater than 1500, it represents the type. See, for example, if it's an ARP frame, there's a number. I don't remember the number, but that if you look at the literature, that number is more than 1500. Similarly, later you will see it can be a VLAN frame. If it's a VLAN, virtual LAN frame, there will be VLAN. This will be indicated here. It's not a normal Ethernet network. It's a VLAN-based network. Okay. So now the next question is, suppose, so this feed value is more than 1500. It's a type, but still we need to represent the length, how many bytes are carried, right? So in that case, the next few bytes, the next 2 bytes will be used to represent the length. If this 16 bits represent the type, the next bytes, subsequent bytes will tell how long or how many bytes are carried here. Again, it's up to 1500. Okay. So we discuss something more when we discuss, we will give more details, more specific details when we discuss LAN, or VLAN. Okay, then you see there is a field called preamble, 64-bit preamble. So whenever an adapter wants to send a frame, first it will send a predefined 64-bit preamble, 8 byte. After this 8 byte, the first 7 bytes will be 10, 10, 10, 10, 10. And the 8th byte is 10, 10, 10, 11. So when the preamble is received by the receiver, okay, it has 2 purposes. One is for clock synchronization. So you can see that 10, 10, 10 is there. So that helps the other party to adjust if there is any drift in the clock between these two, because any drift in the clock may miss a bit or may accumulate more than 1 bit. That could be other dangers, okay? So even though clocks are running at the same speed, they need to be synced. There should not be any drift, okay? So they are used for this, and this byte is used to mark the start of the frame. That means when the receiver receives first 7 bytes like this and the 8th byte is like this, it will mark this is the beginning. Then it will receive 6 byte, then the next 2 bytes will tell the length, how many bytes are carried. Okay? That's how it works. Now, what type of encoding is used in Ethernet? Encoding topic was omitted, right? But in the context of Ethernet, you need to know what type of encoding is used here. Encoding means how bits are mapped to signals. How bits are mapped to signals. How bits are transmitted as signals. How 1 is transmitted, how 0 is transmitted. Okay? So in Ethernet, 1 is transmitted as high signal followed by a low signal. 0 is transmitted by 2 signals, low, then high. So it makes sure that sufficient transitions are there. To transmit 1, it sends first H, then L. To transmit a 0, it transmits L, low signal, followed by H signal. So this is called baud, not bit, baud. Okay? Baud rate, you might have heard baud rate, right? So 10 Mbps Ethernet means 20 million baud per second. It should be twice, because every bit you need to send 2 signal elements, okay, HL or LH. So 10 Mbps, you are transmitting 10 million bits means it has to transmit 20 million signal elements per second. There are other techniques as well. Anyway, we are not going into the details. So this is one of the techniques used actually. So 4-bit out of 5 bits. So there are other encoding techniques. If you look at the book or this, you will know what type of encodings are used. Because when Ethernet evolves, there are many types of Ethernets, starting from the bus, hub, then even fiber. So new standards, new variants are coming up, and encoding can also be different. Now let's quickly look at the Ethernet addresses. Ethernet address is basically 48-bit address, or 6-byte address. So you can check your hardware address, right? Your any system, your computer or tab or phone or anything. So if it has Ethernet adapter, if you can connect to Ethernet, then you can find the Ethernet address. Maybe phone and other things we use mostly wireless, right? Wireless MAC is there. But your computers, PCs, or laptops. So if you look, you can easily check through the control panel or giving command like ipconfig/all, you can find what is the hardware address. It's a hardware address. It's hardwired into your system. It cannot change. So this is an example of the address. Sometimes the notation will be -08-C0-65. So writing 48 bits is very troublesome. So we write it as a hexadecimal hex digits. Is that okay? Broadcast means all ones. That means if a frame is meant for everybody in the network, then it should carry broadcast address in the destination address. If the destination address field is all ones, 11111, all 48 bits are 1, that is FFFF, then it's a broadcast address. It's meant for everybody. And there is also a multicast to refer to a subset of them. Some addresses are multicast addresses. And in the case of multicast address, the first bit is 1. The standard says first bit is 1. What do you mean by first bit? The first bit means this is the first byte. This is the first byte. And the rightmost bit, that is the LSB of this, will tell that is the first bit. Maybe the first bit to be transmitted. So here it ends with 8. 8 is 10000. So it's a unicast address. It's not multicast. But if it ends with 1, if the LSB of the first byte is 1, then it's a multicast address. But our adapter addresses are unicast address. Whether it's multicast to broadcast, it's only when the frame carries that address, not your adapter. So what is happening is this: Ethernet adapter receives all the frames. All the frames which are sent through the cable will be received by our system, but it will accept some, it will not accept others, right? So what are the frames accepted by the hardware or the adapter? All the frames addresses to it. That means all the frames which carry the destination address, which is the same as its own address. Right? Let's say the computer receives so many frames. First it looks into the destination address. If the destination address matches its own address, it will accept and copy it for further processing. Otherwise, it will not accept it. That's how it is manufactured. Right? Then, if the frame received carries broadcast address in the destination address, then it will accept it because it's meant for it also, right? Is that okay? That means if I send an email to you, you will accept it. But if I post an announcement meant for everybody, that's a broadcast. So that also you should read it, right? You can accept it, right? It's meant for you as well. Multicast, if that address, configured, that is, this belongs to that multicast group, then it will accept it. Otherwise, it will not accept it. That is for the user computer. But for the switches, switches also have adapters because they have to receive the bits, transmit the bits, right? In the case of switches will operate in promiscuous mode, meaning that it will accept all the frames. Switches will accept all the frames. And all our adapters, they work or operate in non-promiscuous mode. That means we will accept only those frames which are meant to us or the broadcast frames, etc. Okay? That's how they should be manufactured. That's how they are manufactured. Otherwise, you will capture all the frames in the network, right? And you can manipulate, or you can security and other issues are there. It doesn't allow that. Okay. Now we are ready to study what is called MAC, medium access control, right? So when many systems or nodes are competing for the shared medium, okay? So what's happening? Okay, how? Whether there's a possibility of collision. If there's a collision, okay, what should be done? Say that's a protocol. Here we call it as MAC, Ethernet MAC. So before we look into the MAC, let's define certain terminologies. We say that Ethernet uses CSMA CD, and CS stands for carrier sense. MA stands for multiple access. So I don't need to tell why it's called multiple access. So multiple systems are trying to access it. It's a shared medium. That's what it means. But we have not yet defined what is CS. CD stands for collision detection. So carrier sense means a host, that means a computer. Let's say there's an adapter. It senses the link. It continuously senses the medium, and it can see whether there is any ongoing transmission or not. That is, it can distinguish if the link is free or not. That means, let's say this is a computer. This has an adapter here, right? So it can sense the link. If there is any transmission going on, that means if the bits are flowing here, but closer to this proximity, it can see that the link is busy. But this does not know, maybe beyond, let's say beyond 1 kilometer, okay, there are some bits flowing here. So it cannot sense it. It can sense it, okay, sense transmission closer to this. When the signals, okay, they arrive close to this, they know that something is flowing through the link. Is that okay? And they also, if they transmit, they can also hear it. Something like when I speak, I hear. I also can hear if other people are talking in the medium, right? But I cannot hear somebody maybe is talking at the further end and all. I cannot hear it, right? Similarly, if the bits or signals flow closer to this, they can sense. Why this property is required? Because if they know that there is some ongoing transition, then they should not transmit. There's no point. If they transmit the frame, there will be collision, correct? It should be intelligent enough, at least to that extent. Collision detection. If there is any collision, it should be able to detect it. But the mechanism is simple, okay? A host, when it transmits, because it's interested to detect the collision when it is transmitting, right? Let's say it's transmitting a frame, so you should make sure that its frame is not collided, right? Its frame transmission is successful. So if there is a collision, because it can also observe the signal strength when it is transmitting. This is something like when I speak, I know the voice strength, okay? So if there is where the signal strength or power shoots up, then it will understand there is a collision. So when this is transmitted, let's say first it was probing here, sensing here, no transmission, but there was transmission at the further end, but it doesn't know, so it starts transmitting. So when it starts transmitting, okay, initially for some time, that's fine. It can hear whatever it transmits, the signal strength, okay? But when these bits, signals move, when they come closer to this, they will collide with the signals transmitted by this adapter. Okay? So then there will be a signal, the signal will shoot up. So by observing that, it will know that there is a collision. Then it has to act. We say that Ethernet uses what is called one persistent CSMA. So then we need to define what do you mean by persistent CSMA. In general, P persistent CSMA is this. The question is, if a host is ready to transmit a frame, let's say this is the computer, I have a frame to transmit. Can it send immediately? Of course, it sends us the channel. If the channel is free, can it send immediately? If the channel is free and if it sends immediately, assuming that nobody else is transmitting, then it is one persistent. With probability 1, it is transmitting. But even after finding that the channel or link is free, and then it wants to be cautious. Even though I find link is free, there's a chance that somebody else may also think the link is free, right? Or there may be transmission at further end, okay? So that means it's not very optimistic. This wants to be more practical, okay? In the name of practical, it wants to defer its transmission. Then in that case, it transmits with probability P. It transmits probability P. So what do you mean by, let's say P is 0.9. That means this is something like similar to, it generates a number from 1 to 1000. If it gets number 1 to 900, it will transmit. If it gets a number from 901 to 1000, it will not transmit. This, I mean, I just try to give a simplified example, okay? Is that okay? So even after finding the link idle, if it transmits with some probability P, then we say it's a P persistent CSIMA. But Ethernet transmits with probability 1 whenever it finds the link is free, unless there's a collision. Okay, that we will see later. Now we are ready to explain the MAG. Okay, in other words, okay, how and when the transmission takes place. Let's say that's a host, it has a frame to send. What it will do first, okay? There is no coordination. That means it's not worried or it's not concerned whether somebody is transmitting or not, okay, or somebody wants to transmit or not, okay? Instead, what it does is it will sense the line. If the line is free, line means link, okay? It senses the cable. If Y, it checks whether there is any transmission close by. If it finds that, okay, some bits are flowing through this, signals are flowing through this, then it will not transmit. If it finds that the link is idle, then it will send the frame immediately. If there is no collision, it can send up to 1500 bytes. That's the maximum frame size, okay? But if it finds that the link is busy, obviously it will wait, but it will continuously see, okay, when the link becomes free, correct? So when the link is busy, there's no point in transmitting. The problem occurs when there's a collision. When there is a collision, okay, when the collision is detected, then it has to act. Okay? So then it thinks, okay, why there's a collision? Because there are many active users. Initially, it thought he is the boss. He is the only one who is transmitting. Nobody else is transmitting. So he simply starts transmitting, right? But if there's a collision, there is at least someone else who is also trying to transmit. So it tries to estimate the number of active nodes or how many people are trying to transmit at the same time. If it thinks many people are trying, then it will use a small probability, or it may have to defer. How long it has to defer an attempt, retransmission attempt, that depends on how many active users are there. Okay? And again, there's no coordination among all the nodes or hosts in the same network, Ethernet. So it uses a very simple backoff algorithm, which we call it as binary exponential backoff algorithm. So initially it is optimistic in the sense that if there is a first collision, let's say this is the first collision for it. So that means the previous frame transmission was successful. First time it is colliding. Okay? Then it is optimistic. It thinks that there are only active users, including itself. There is only one another user who is also trying to send. So what it does is it estimates the number of users as 2. So it generates a random number from the interval 0, 1. It chooses a number 0, 1. If it gets 0, it does not wait before it senses the cable. If it finds the cable free, it will transmit it. But of course, it has to see whether there's any ongoing transmission and all. All the bits should be drained. at least the link or cable closer to this should be free, okay? If it gets 1, it waits for 1 time slot before it makes an attempt or before it senses the cable and start transmitting, right? And 1 time slot here is 51.2 microseconds. So later you'll understand how you get this number, magic number 51.2 microseconds. But at this time, okay, you assume that it is slots. So how many slots it has to wait or it has to back off before it makes a new attempt, okay? Now, the optimistic assumption is that if this host gets 0, the other fellow will get 1. If the other fellow will get 0, he will get 1. That's very optimistic, right? That is a chance. But there's also a chance that both will get 0. There's a chance that both will get 1. So there could be, when they transmit again, there will be another collision. That's a possibility, right? So if the collision is a second collision or second consecutive collision, that's important. Once it is successful, the collision count will be reset to 0. So second time, but since a consecutive, last frame was not successful, this frame is also not successful. It's a second collision. Again, there's a collision, okay? Then it adjusts its estimate. So earlier it was thinking that there were only 2 active users. Now it will assume that there are 4 active users. It doubles the estimate. It thinks that there are 4 active users currently in the network. So then it generates a number randomly from the interval 0 to 3. If it gets 0, it doesn't wait. If it gets 1, it waits for 1 time slot. That is 51.2 microseconds. If it gets 2, it will wait for 2 time slot. If it gets 3, it will wait for 3 time slots. It assumes that different hosts will get different numbers. But still, there are some combinations for which there will be another collision, right? So there's a chance that there will be a third collision. So first collision is 0 to 1. Second collision means 0 to 3. Third collision is 0 to 7. Then it triples the estimate. It thinks that there are 8 active hosts, including itself. So it generates a number from 0 to 7. Accordingly, it differs or it backs off. In general, if it is ith consecutive collision, the interval will be 0 to 2 raised to the power I minus 1. Okay? When it reaches 10, it will become 0 to 2 raised to the power 10 minus 1, so 0, 10, 23. Because the maximum number of hosts within a single Ethernet network is restricted to 1024, even if I becomes greater than 10, the estimate would be 1024 only. It won't go beyond that. And it makes attempts, repeated attempts, but if it exceeds some numbers, let's say 16, it gives up. So it assumes that there's a serious fault, so it aborts. Any doubt in the MAC? Yes? Yes.
So do they allocate this number to different hosts?
No, it doesn't allocate. No coordination. Okay? This algorithm is only for this computer. Okay? So for us, maybe, okay, for this computer, it may be the first collision. But maybe for the other computer, it may be the second collision or third collision. So he will be generating number randomly a different interval. So this is with respect to only this host. For this is the first collision. Then second consecutive collision, consecutive, right? Once it is successful, collision count will become 0. First collision for this doesn't mean that it should be first collision for others also. Yes. So that's why it's completely local. There's no coordination among the others. So from that perspective, it is very simple. The algorithm is simple. And it has been shown, theoretically as well as experimentally, that it works well. It works well, okay? So there's a simple probabilistic method, random-based method, but it works well, and it's a very simple algorithm. Simplicity always wins the market. So this also has been quite, is one of the reasons the MAC is simple. If you look at the other one, token-based one, though it looks simple coordinating among everybody to have only one token so that there's no collision, right? The token ring. The token management is a big complex issue. Any coordination is a complex issue there, okay? So here there's no coordination at all. So later, yeah, so this will be covered in last week tutorial, okay? So you see that some interesting problems are there. Okay, Ethernet constraints or imposes some limit, okay? The frame size should be minimum this many bytes. You cannot send just 1 byte, 5 bytes in an Ethernet frame. Okay? So we say that it should carry minimum 64 bytes, including 14 bytes of header. Why 14 bytes of header? 6 byte for destination address, 6 byte for source address, 2 byte for the length or type fields. So 14 byte header, and you should have minimum 46 byte data and 4 byte CRC. So this and this are fixed, 14 and 4 are fixed. So in terms of data, it should carry minimum 46 byte data. If it doesn't carry 46 byte data, then we need to add some dummy bytes. Yes?
What is the range? You said that when there are bits on the link, it sort of sense that there are them. What is the range of the sense?
Range will not be very big, few meters only.
Then what is it that limits the max length of the Ethernet?
Max length of the Ethernet, okay. What is max length of the segment? Maximum length of the segment is limited by the physical characteristics of the cables, right? If you use a thick coaxial cable, after 500 meters, there's a high chance that the bits will be damaged. The attenuation so poor. So we have to limit the the length of the segment. That is limited by the cable properties, okay? The physical medium properties. But how many segments we have, okay, that's a standard, okay, by the network community set together and decided, okay, we can have 5 segments. Theoretically, there's no limit. You can have more than 5 as well, okay? Is that okay? Yeah, maybe at that time they might have thought, okay, maybe typically in a company or university, okay, how long we need, right? There should be some standard, okay? But later we see that if it exceeds, if you want to have more and more, okay, then we can use bridge and switches to make it longer. Okay, yes?
Then in the case for Manchester encoding, why do we need to transmit the low signal after the high signal if the clocks are already synchronized?
Okay, so low followed by high is for 0, for 1, high followed by low, right? So the problem is, okay, I didn't discuss much, okay, suppose you have a long sequence of ones or long sequence of zeros, right? If you don't use it, let's say you want to transmit 1 means high, you transmit only high, right? The clock synchronized for a frame in the beginning, right? But it carries 1500 bytes. It carries 1500 bytes. Let's say we are trying to send all ones in the frame. So 1500 means how much? 12,000, right? 12,000 bits. Okay. So if it's a long sequence of ones, if you don't have transition, what happens? There will be H, 10,000 or 12,000 H will be there. Correct? So if there is a thousands of high, without any, the transition was there in the beginning when you send the preamble 1010. But after that, there is no transition, all flat high. So then there's a chance that there could be a drift, okay, because there's no transition. Because the bit starting, where the bit starts, it should coincide with your clock transition. And also the adapter, okay, to to differentiate 1 and 0, it uses a threshold. When it receives a signal, okay, how does it know that it is low or high? Let's say the signal is already attenuated. Okay? Let's say 1 means high, 0.2 means low, see for example, okay? So when it receives 0.5, when it receives a signal 0.5, 0.5, how it should interpret, whether it should interpret it as 1 or 0. Do you get this point?
Yeah, but then in the preamble, you send.
So, wait, let me complete. So, what happens is, depending on the bits which is receiving, right, and it continuously when it receives bits, okay, the threshold is dynamic kind of things. So, if it receives continuously same bit ones or zeros, the threshold, okay, will be adjusted. So, if you have a high threshold, okay, let's say instead of 0. 0 is the highest, right, originally. Let's say you set 0.6 as the threshold for 1. Then, when after some time when you receive, let's say the next frame, you receive a bit, okay, 0.5, okay, and 0.5 will be considered as 0, okay. So that threshold maintaining is also important. That's why it makes sure that sufficient transitions are there. Yes, any doubt?
So, but then in the preamble, you have 1010101010 used for clock synchronization. How does the receiver know that it's not 01010101? Because 10 is high and low. But then how do you know that that low before the high is not considered as a 0?
That is the from preamble, right? Once the preamble is recognized, once the preamble 8 bytes are recognized, only then the frame starts.
But like how do we recognize the preamble? Like if the 1 in the preamble is sent as a high and then a low,
Yes.
then I assume that the link is.
So let's say a frame is received, okay? Usually there will be, even though we say that's continuously sent, there will be a silence period, okay? So now it's it's looking for the second frame, right? When it looks for the second frame, first it will look for the preamble from the receiver side. So when it is done with the first frame, now it looks for the preamble. That means the next bit it will be expecting will be 1, right? It knows the preamble, okay? So that's 7 bytes followed by the 8th byte. Once it is received, then the actual frame, the destination address starts. Right? But there is always a chance, okay, maybe a very, very, very small chance that still we may come up with an example or the signal is so poor, this, that, right? So that's why I said there is always a chance that may be dropped, okay, good frame may be dropped or something. Then the so-called, or even if the error goes undetected, it's okay. So there will be further detections in IP layer as well as IP as well as TCP also. Okay. Of course, I think IP version 6 I think it has decided not to do that. If I'm not wrong, let me confirm it. But most of them are IPv4. Okay. But that's why I said, if it is dropped unnecessarily, it's a good frame, it is dropped, no issue. That will be retransmitted at TCP level, right? But if it's a bad frame, declared as a good frame, it will go through further tests subsequently at different layers. So there's high chance that it will be detected. But nobody guarantees 100% chance. We cannot. I don't think there's any algorithm which will 100% guarantee that all type of errors will be detected. No. So now we are going to look at why there is such a limit or constraint that it should carry 64 bytes. So suppose we want to carry less than that, okay, then that means there will be dummy bytes. There will be dummy bytes, okay? But how we know the dummy bytes? Because the length will tell. If the length is less than 64 or 46, okay, 46 bytes or something. So instead of 46, if the length tells only 30, then the remaining 16 are dummy bytes. That's very simple, okay? Now the question is why there should be such a constraint. Okay? So if this constraint is not imposed, there may arise a situation when the sender has transmitted the frame without detecting the collision. It may so happen that the host has sent the frame. Let's say the frame transmission is very short. The frame is very short and the transmission is very fast, very short. It may so happen that this host has completed its transmission, that is the last bit has been transmitted, but the collision happens after the last bit is transmitted, correct? In that case, it doesn't know that its frame has collided. Note that there is no acknowledgement or negative acknowledgement in this Ethernet, the broadcast context, to tell that your frame has collided or not, no, okay? Now look at this illustration. Let's say A is sending a frame to B, which is on the other side. The extreme side means after 2.5 kilometers, there is another computer. Okay? So this is the first bit, this is the last bit. So the bits are propagating, traveling towards B. So B, just before the first bit reaches B, B wants to send something, because that can happen, right? So then it senses the cable closer to this, and it finds that okay, there's no transmission going on. So B thinks that the link is idle. The link is free. So B starts transmitting bits. So this will be moving further. He is also transmitting. So B will know, okay, then that's a collision, correct? Because these bits are moving further, he is moving further. So these bits will be receiving. He is also producing the bits. So there will be a collision. The signal strength will shoot up. So it knows that there's a collision. So when there's a collision, it stops its transmission. Okay? And it stops its transmission. Maybe one thing I forgot to mention, when it stops transmission, it will send a special jam signal. Anyway, I will come to it later. But it stops, let's say it stops its transmission. And it sends a jam signal. The jam signal is a special, of course, it has, sorry. If there is a collision, it transmits 32-bit jamming sequence or signal along with 64-bit preamble, then stop transmitting frame. So whenever there is a collision, what a host will do is, it will not suddenly stop its transmission, okay? So it transmits a 32-bit. 32-bit, okay, does not carry any information like, okay, there's a collision, negative acknowledgement or anything. Just as random bits, that's how you can assume. Along with the 64-bit preamble, then stops. Why it's doing that? That answer I'll give later. So this illustration tells the jam, it sends a 32-bit jam signal that reaches A. But by the time the signal comes back, A has already stopped its transmission. A has stopped its transmission here itself. So all these bits are moving here. It's detected there by other person, but not detected by A. A is happy because it already transmitted, right? Unless collision happens around this region, A does not know that it has collided. Correct? Is it clear or not? So that means when the jam signal comes back, it should still be transmitting. The frame size should be such that TF is such that it should be at least RTT. Because within one RTT, the jam signal or the front end of the jam signal will come back. Correct? If TF is greater than this, that means the A is still transmitting the frame. And in that case, it will collide with this jam signal. Correct? It should collide. Otherwise, we cannot detect it. So this condition should be satisfied. Is that okay? TF should not be so small, it should be big. That means when the jam signal comes back, A should not have transmitted its last bit. Still it should be transmitting some more bits. So this condition should be satisfied. If this condition is satisfied, even if its frame collides at the very far end, still it should be able to detect it, because that fellow will be throwing out some bits. So with those bits, it will be colliding. Okay. So what is TF? TF is size divided by bandwidth. Size divided by bandwidth. That will be RTT. Now let's say the bandwidth is 10 Mbps. That was the first Ethernet, okay, standard, 10 Mbps. So in that case, size should be 10 multiplied by 10 power 6, 10 Mbps, multiplied by RTT. The longest possible RTT in an Ethernet is bound by 51.2 microsecond. Okay, because the longest Ethernet can be 2.5 kilometers, right? And the signal should traverse 2.5 kilometers all the way here. And the worst case, there are 4 repeaters in between. It has to go through the repeaters. It has to be repeated, regenerated, kind of thing. There is some delay inside the repeater also. And on the way back, again, it has to traverse 2.5 kilometers, and it has to go through the repeaters, right? And the delay is upper bound by 51.2 microsecond. It can never exceed 51.2. It may be smaller, actually much smaller than 51.2, but to be safe side, 51.2 is set as the upper bound. Okay, so size should be like this. That means size should be 512 bits. That is 64 bytes. That's why 64 bytes size limitation is there. If it transmits at least 64 bytes, this situation will not come. When B detects and it throws out jam signal, that by the time jam signal is received, still this fellow will be transmitting its frame. So it will know that its frame has collided somewhere. It doesn't need to know that it has collided with B or C, right? Okay? Is that fine? Now the next question is, why we need this jam signal? Let's say B detects the collision, or whoever detects the collision, why it should throw a new 32-bit through the network, right? It's a jam signal. Note that this jam signal doesn't have, okay, these bits mean acknowledgement bits or this, no, just some 32 bits, okay? Why? Because if it doesn't send any jam signal, this will be still transmitting. The collision has occurred here. Let's say B has transmitted only few bits, and it has found the collision. If it stops its transmission, nothing, it's not throwing out anything. So A will not have sufficient energy to detect. Okay, something should come back. Okay, only then when it collides, it can see the collision, right? So that's what is written here. If B terminates its transmission after sending only a few bits without the jam sequence or jam signal, host A may not receive sufficient energy to detect the collision. That means B is throwing away some stones. He is throwing away some stones. B should have sufficient number of stones. Only then it can hit and it can hear the sound. Any doubt? Yes.
Why not we do the same thing with the delay? Why does it have to keep transmitting?
Which one?
Why does host A have to keep transmitting for 62 bytes? Why can't they just wait for a while and then the jam signal arrives?
When the jam signal arrives, how does it know there's a collision?
Because if it receives a jam signal, it transmits and then it just waits for the jam signal to arrive.
Because jam signal, even if you define the bits for the jam signal, okay, may also collide with some bits here, correct? Jam signal, by the time when it is received, don't think that jam signals will be intact in terms of bits. It's just a group of bits. Do you understand?
That's okay.
But it does it, so what you are saying is, okay, let it receive the jam, right? And it checks, okay, it should check and recognize that it's a jam.
What I'm saying is that the reason the 64 bytes exists is because of time. Because this period of time is required for the signal to reach the end.
Yes.
So if we already know the period of time, why do we have to waste bandwidth and transmit those number of bits instead of just waiting for that period of time to see if a jam arrives?
But how does it know jam arrives?
A jam would be any, say, 32 byte signal that it receives, but why do we have to transmit only 64 bytes and nothing else? Like, why can't it be smaller?
Yeah, okay, I understand it, but when jam receives, okay, it cannot recognize that it's a jam signal. It cannot go and see, okay, what are these bits in the jam signal, because there's no guarantee that the jam signal bits, when it is transmitted, is the same when it receives. Do you get this point?
Yeah, that is okay.
So there's no way that even if it waits for a few microseconds, let's say it stopped its transmission, then you wait for some time, that's what you are saying, right? Then you see whether any jam signal comes or not, right? Okay, so then but it should know what is the jam signal, right? It should know the bits in the jam signal.
Why is it necessary? Why can't it just do what it is doing now? Like it just sees whether a 32 byte packet arrives or not, regardless of what it is saying. Why can't it do the same now with just waiting?
Okay, now what it's done is, some bits are received, it's transmitting, collides, it detects the collision, correct? What you suggest is, it will be, right, when the jam signal is received intact by A. Intact means without missing any bits, without anything. If jam signal is received by A, should be fine, correct? See, for example, instead of 32, even if it receives 30 bits or 31 bits, still it can detect it. It throws away, right? Because that jam signal will also go through the remaining bits, because this frame is also going further. Do you get this point? And also it must so happen that, this is an example, okay? There will be collision with multiple things also. Let's say this is C. This may happen here also. Let's say B and C are close. B and C both can detect collision also. Both also will generate jam signal. Do you get this point? So B and C will generate jam signal. So there is no guarantee that the number of bits and what bits are there in the jam signal will be received at A. What A requires is some bits should be received, right? So that bits, whether it's a jam signal or it's a valid frame and all, it's not distinguishing it. If it can distinguish that this is a valid jam bits, it's not a frame bits, okay? So that's very difficult, because, okay, in this example, there's only one jam signal. But it may so happen that, as I said, if the collision happens with C as well as B, both will be generating jam signal. That's good. A can receive some bits from the other side, it still transmits, it can detect it. But if it tries to read the bits and count the bits, it doesn't work. Is that clear? Maybe let me finish another small topic before we wrap up. I think we are running late. Okay, as I was mentioning, so whatever we discussed is with respect to shared medium bus, which were popular in 80s or late 70s or 80s until early 90s. Then hub was developed, hub Ethernet was developed, they become popular. Then in 2000s onwards, switches, they are called switching hub or Ethernet switches, they become popular. So let's do a quick comparison between all. First, we start with shared medium bus. I think this we have discussed enough in the beginning of today's lecture and the previous one, okay? And we don't need to discuss again, but only one terminology, okay, we will introduce in this context, that is single collision domain. We say that it has single collision domain. Domain means set, in the sense that any host can collide with any other host in the same set. This is a collision, possible collisions, correct? Because all share the same bus. A can collide with B, C, D, similarly D can collide with this, right? So we say collision domain is only one set, which will have all the hosts. That's the meaning of collision set. So anyone in this set has a possibility to collide with anyone else, okay? And also if there's a cable cut, something like this, don't think that it will work as two different Ethernet, it will not work. So why? Because we need to terminate the signal here. If there's a cut, this will become malfunctional. Next, evolve hub-based LAN, okay, and it uses star configuration. So this is a hub, a box with multiple ports. Okay. Then to this hub, all these hosts are connected. So what, okay, this uses star connected topology. That means all are directly connected here. It's not like a bus, linear bus, okay? And this also a broadcast medium. What it does is this. Whenever a hub receives bits from a host, let's say B is transmitting. Whenever a hub receives bits or signals from one port, it will simply copy to all other ports. So these bits will be copied here, copied here, copied here, internally. Mechanically it will do it. It doesn't look into what is the destination it does. Whether B is trying to send it to C, A, D, it does not distinguish. Whatever bits received by B, it will copy into all the remaining ports, direct to all the ports. Similarly, when it receives from D, it will copy into all other ports. So eventually it's a broadcast, and there is a possibility of collision as well. Okay? It uses, the example is 10 base T, and 100 base T is also possible. 100 base T, 100 stands for 100 Mbps. The name for this is fast Ethernet, because at that time, in 90s, okay, 100 Mbps was seen as quite high. Okay, compared to 10 Mbps, 100 Mbps was very high. So it was called fast Ethernet. And, but because it's a broadcast, it also suffers from all the other drawbacks. But here there's no question of cable cut. If cable cut means the cable which is connecting the host, like a LAN cable, to this, okay? So that means the cable cut means, so this, only this host is out and all other hosts will work normally. Okay? And this is seen as a better configuration than bus, laying out the bus here, because you keep it, the hub in a convenient place in a room or the lab, and you can have wiring, okay, to a convenience. And you don't need to have a 2.5 kilometer long, because that's linear communication. It's a star connected. So the distance between any two, A to D or A to B, is more or less same, because the distance from A to B, D to the hub, or A to hub, is more or less same. The distance is A to hub plus the length of the hub, then hub to D, correct? This is more or less same as A to B or B to C or anything. So we don't need to have constraint like 2.5 kilometer and all. Then evolved switch-based LAN. It's called switch hub or switches. Okay? Switches, if you recall, okay? A switch, what is a switch? It has multiple ports, 1, 2, 3, 4, okay? And what is switching? The process of forwarding data from an input port to an output port. It's not broadcasting, okay? It will directly send it to only one port, okay? And the switches usually use full duplex. That is, when A communicates to B, B can communicate to A. So if you look at this example, let's say B sends some data to A. At the same time, C will send data to D. Why? Because the switch, okay, is more intelligent than the hub or bus. Hub and bus are very dumb devices, okay? So here, it looks into the header. The switch will look into the header. It knows that, okay, this is the destination address, and it has a forwarding table. Forwarding table. This will tell, okay, what the destination address and port number. So when switch receives frame from B, it looks into the destination address. If the destination address says it is meant for A, then it will forward only to A. Okay? Is that okay? Similarly, when it receives from C, it looks into the destination address, it considers the local forwarding table, and it knows that this can be reached through this particular port, then only it will send it to that particular port. Note that when B sends to A can send to B. When B sends to A, even C also can send to A. Why? There are buffers inside. Whenever a frame, it uses statistical TDM, time-dish multiplexing. It has buffers. Whenever a frame is received, that frame is put in the buffer. Then it will be released one by one. So when B sends to A, C also can send to A. There's no question of collision and other things in a switch, right? So in the extreme case, all the 4 hosts can be transmitting, all the 4 hosts can be receiving. So if there are n hosts, the total capacity will be n into 10, assuming that each adapter operates at 10 Mbps. So in this case, in 1 second, it is possible that A can transmit 10 million bits, P can transmit 10 million, C 10 million, D 10 million. So total 40 million. The throughput can be 40 Mbps. So throughput is 40 Mbps. This is the total throughput. Okay, in the broadcast LAN or bus-based LAN or hub, it cannot be. Okay. Why? At a time only one can transmit. Here multiple transmissions take place. It also uses star configuration. So switch, small switch you can assume, if you want, you can look at the book or internet. Okay, it will give you the pictures of the switches. Large switches are also there with line cards and other things. Big switches or small switches. You can assume that there are ports to which the systems can be connected. So it also uses star connection, star configuration. And fast Ethernet can also come with a switch switch topology. We can have fast Ethernet with the switch as well. And there are also other standards, okay, which supports optical transmission. See, for example, 802.3. 802.3 is the basic for traditional, the bus-based one. So these are all the variants, 3U, 3Z. 3Z is for gigabit Ethernet, which supports the optical port, fiber port. Okay, so port means you can transmit through the fibers. So there are 2 standards, 1000 base SX, 1000 base LX. 1000 stands for 1000 Mbps, 1 Gbps port. And SX stands for short wavelength, because optical transmission, the wavelength. So there are 3 standards actually, 0.85, 1.3 and 1.55. Okay. 1.55 is used for WDM. I think the first lecture or second lecture I mentioned, wavelength division multiplexing. Okay, so recent optical network, particularly wide area networks, not local area network, they operate at 1.55 micron. And 0.85, 1.3, okay, we can use the Ethernet or SONET and other things. So the operating wavelength is 0.85, it's a short wavelength. 1.3 is LX. So short wavelength uses multi-mode fiber. Single mode fiber is used, okay, with the standard 1000 base LX. Okay, as I said, it uses store and forward. That means it has to be stored, then forwarded. And you can see that there's no collision between ports. A cannot collide with B, B cannot collide with C. But if you have a switch, and if you connect a hub, or let's say bus-based LAN to a port, then within this hub or bus, there can be collision. But a packet or frame from A cannot collide with B or C or this, because inside there are buffers, one by one they are released. So we say that the collision, if at all, happens only within the port. So if you connect only one computer to this, collision with A means there's no collision, right? But if you connect a hub to a switch, within the hub there can be collision. We say that within one port there can be collision. So this shows, this is the last slide today we discussed. This shows a typical configuration in a campus. Of course, it's a simplified configuration. Okay, at the lowest level, we can have Ethernet hub. Nowadays, I don't think we dominantly use or we use the bus-based Ethernet. So hubs can be used at the lowest level. And at the next level, we can use switch which supports, let's say, 100 Mbps switch. Okay. And these colored lines represent different capacity or different data rates, 10 Mbps, 100 Mbps, 1 Gbps. So at one stage, we have servers in the data centers or the computer center. Nowadays, we call them as data centers. So data center servers are connected to switches with high-speed links, 1 Gbps or 10 Gbps, 40 Gbps, etc. Okay? So this shows the capacity of the server, because he is the one who is serving more users, right? So let's say university server or any organization, they have their own server. So if you look at the switch, some ports are 100 Mbps ports, some ports are 1 Gbps ports. So you can have 1 Gbps port, fiber port, and normal 100 Mbps port. And so at the highest level, there are multiple servers connected to the switches. It's not one switch. Actually, there is a rack of switches in the data center. So many switches are there, but it's a simplified diagram. And this could be part of one department. This can be another department. Okay, so this is how they are all connected in an organization. Okay. So this shows a typical configuration, although it is simplified or scaled down. And as I said, hubs are also nowadays, people, they don't want to use hub because the switches are becoming cheaper and they can provide higher throughput. So we directly go for switches. Let me stop here. So we'll meet again next Monday to complete the lectures. Of course, we are slightly lacking. Hopefully, I'll be able to complete. But this Wednesday, we will discuss tutorial 3. Let me stop here. So if you have any doubts, I'll be happy to stay for some more time. So others may please leave.